Ladies and gentlemen, good afternoon. It's our pleasure to invite Professor Härdle to our school. Today, Professor Härdle will give us a talk. This topic will focus on statistics in finance and computing. To my knowledge, Professor Härdle teaches in the Department of Statistics, University of Humboldt-Universität. He's very famous and excellent in the field of computational statistics, especially in the application of finance and computing. We have 3 hours for today's lecture, and a coffee break at 3:30. Now, let's enjoy Professor Härdle's lecture. Thank you so much, and welcome, Professor Härdle.
Thank you very much. I'm sorry for the delay. It was entirely the heavy traffic in a well-working economy, right? So the network was overloaded. But almost everything has been said by the chairman, but some of you may not know me that well. And that's why I would like to present you my webpage. Actually, I'm not from the Department of Statistics. We have a different structure. In Germany, we have a department called Department of Economics and Management Science, or in German word is Wirtschaftswissenschaftliche Fakultät. So if you want to see my webpage, you have to go to ISE, or Institute for Statistics and Econometrics, ISE. Please note it. I'll write it for you down here. ISE.wi, ISE, Wirtschaftswissenschaften, HU minus Berlin.de. Okay? Now, inside the Institute of Statistics and Econometrics, there's a chair of statistics. That's my chair. And we have, of course, staff. And you go to staff. This will take a little bit longer because this file is loaded from some other place. But it will come in a second. Can you see this pointer here? Mm-hmm. Also from behind. Can you see it? Really? Okay. So what's this? What's this letter here? See, you could see it. What's this letter here? It's too funny. Maybe after the break I need reference. Okay, this letter is called A umlaut. Okay, and here you see my web page. It's updated since yesterday with some Chinese name card here. You can see my name in Chinese, and you can see that I am international advisor of the Guanghua School of Management at Peking. And you see also, let's start this talk with a little bit of pattern recognition. You see an old picture, and you see many people there, but 3 people in the foreground. Who do you think is me? The middle guy with the suit, right? No, there's no guy with the suit. The middle one, yeah, that's right. The middle one, that's right. That was about 34 years ago, and I was making the high school diploma at that time, and 34 years ago we were protesting against the numerus clausus. You know what that is? You have entrance exam if you go to universities, right? We have an inverse system. The high school diploma, the score of the high school diploma serves as the score that allows you to study certain fields. Right? For example, medicine had a numerus clausus. It's a Latin word that says that sets a limit on this score. Yeah? And I wanted to study originally medicine. That's why I started not medicine but mathematics. For 1 semester later I got the score, so I could study medicine, but finally I decided to stay with mathematics. So this is how I look like today when I'm coming back from a soccer or from a bicycle ride. You see my Härdle number. If you're interested in that, just click on the other stuff, you see a little bit my history. It goes through Peter Huber or Gerhard Schmidt, Hilbert tells you anything? Hilbert spaces, Gauss, normal distribution, it goes up to 1668, so after that I don't have more data. You find this kind of mathematics genealogy project here under this web page. You find the books and proceedings. Just recently, the book by Stefan Sperlich and Härdle came out, The Art of Semi-Parametrics. Last year we had statistical tools in finance and insurance, and newer articles you find also on this web page. I'm just showing you where to find this talk. It should be somewhere around here, Statistics in Finance and Computing. This is this channel. So you find this talk, and also this film, which is in Apple QuickTime format. That's why we had to change the computer. Yeah? I'm sorry for that. But also this gives me the chance to show you more on the software that we developed called Explore. Okay, so now let us come to the talk itself. Let me try to say this correctly here. This should mean risk. So I hope this is correct. But I forgot the Chinese pronunciation for chiffon or feng shui or something. Yeah, we see here the word risk associated with financial markets on an example of I think Shanghai development of the time series. Now this talk it can actually be given for, when I gave this talk last time as international consultant for the ADA School of Management, I had only 1.5 hours. So today I will extend it because I have a younger audience here to 2.5 hours because we're already late or a little bit less. But it can be extended even more. So essentially it contains thoughts and research lines that we have followed through the last 5-6 years on 4 different topics. And one topic is, and that's why this film is important, is to model and estimate implied volatility surface for trading, hedging of derivatives, and to understand the risk behavior of a very liquid market. And this is a joint work with Michael Benko and Matthias Fengler. Michael Benko finishes now his PhD thesis, will go to Deutsche Bank. Matthias Fengler already is since 2 years at Oppenheim. He has written a very nice book in Springer Verlag on implied volatility modeling in a semi-parametric way. It came out last year. Then I will show you how to calibrate the IVS, this is the implied volar surface, and price options with the fast Fourier transform. This is a chapter in the book on statistical tools in finance and insurance. This is joint work with Shimon Borak and Kai Detlefsen. Kai Detlefsen is also Kai Detlefsen is also a Oppenheim PhD student. Shimon Borak is my institute. And then finally I will show you how to do the GANA, that means how to estimate value at risk with generalized hyperbolic distributions in an adaptive way based on local homogeneity ideas. And this is joint work with Yin Chen and Seok Oh Yong from Korea. And if I have time, I will talk to you about skewness and kurtosis trading strategies. This is a cooperation with investments. Okay, now let me first talk to you about implied volatility string dynamics. Implied volatility string dynamics means that I try to quantify and model over time a phenomenon of this type. You see here, for the moment, we see here sort of a towel that moves in time. The red points here, the stick. The red points denote implied volatility. We'll define it in a second. And you see as we move here along, this is this is August 2001. We are close to 9/11. We are coming to 9/11 in a few nights later, you come here, 9/11, you see, the shock of the 9/11 accident. We want to understand this kind of dynamic over time. Yeah? This is called implied volatility dynamics. Okay, so what did you see? What were the red points? Do you remember what I said, what the red points are? No? Anybody else? Okay, I have to speak slower. The red points were the implied volatility. But how is implied volatility defined? Implied volatility is defined through Black-Scholes formula. So everybody knows the Black-Scholes formula, certainly. Yeah? But also, please. You have a question?
Microphone.
Microphone?
I mean the wireless.
Ah, okay. Good. Thank you. Thank you very much. Hello? Hello? Very good. Okay, thank you very much for the suggestion. Okay, everybody knows the Black-Scholes formula here?
Yeah.
Very good. The underlying stochastic process is called a geometric Brownian motion. Okay? But it has a fixed constant volatility coefficient. Under this underlying geometric Brownian motion, this fixed volatility coefficient, I can derive the so-called Black-Scholes formula for a call, time t, with maturity capital T, and volatility sigma, and strike price k, and constant interest rate R. I can derive this call price. But I can also see on the market the call prices, the option prices, and then try to equate the Black-Scholes price, the theoretical price, as if the underlying process were geometric Brownian motion with what I see on the market. And what's the answer? Is sigma constant? Is sigma constant? The answer is here. Sigma is not constant. Sigma is not constant. The red points are exactly those sigmas that I've calculated for different maturities and different moneyness. That means different strike. This is maturity. So this is half a year. This is half a year, 6 months here, and this is at the money. This is moneyness at the money. This is 1.2, 1.8, corresponding to out of the money. Okay. So volatility is not constant. Okay. Now, and this together, when I observe such a grid on K or moneyness, strike, and maturity, then I can ask myself, how does this grid move in time? That's what you saw in the film. So one more time, in the film you saw the implied volatility as a function of K and tau moving in time. Yeah? And there's 9/11 again, and my first topic will give you a model for fitting this dynamic in time. Yeah? Okay, why are we interested in implied volatilities? They are easily observable. Actually, traders like to price in terms of volatility. You can define trading rules and trading strategies through implied volatilities. There are tradable volatility contracts like the VDAX or the VIX, or now the new DAX V1X. And what is the purpose of our study? The purpose of our study is to understand the dynamics of this red points over time. Yeah? We saw this blue curve inside there, and this blue curve is a so-called smooth surface. We'll try to smooth the surface over time, and for that we use a model that is very close to principal components, so-called a dynamic semi-parametric factor model. It's a semi-parametric factor model because the factors are these functions, unknown basis functions, and the loadings of the factors are loadings called beta IL. are moving in the beta Is that are moving in time. So I here is the time index, yeah? So I is the day and J is the intraday data. Okay, so the idea is to use a modeling and estimation in one approach and fit these beta Is that allow us then later to correlate it, for example, with macro variables or define skewness detection strategies there. Okay. Now, first of all, there are a few difficulties with this design of IB data. You have, for example, here on the 2nd of May 2000, you have this situation. This is typically called an IB smile or smur, right? And you have, when you look from above, you have this data design. So the point is, you cannot use, and you have seen it also in the film, you cannot just use an estimator for each day, because some point you don't have data at all, and some points you over-smooth, you see you don't get this fit right. So with the blue surface that you see here is a smooth surface every day. So by understanding that the design, of course, the tau will move in this direction over time, because the contract expires, we smooth also, that's the idea, we smooth also over time. So what you have seen in this film, where sometimes the blue surface sort of broke up into very small little pieces, we will show you how to model the whole implied polar surface in terms of a so-called dynamic semi-parametric factor. Here's the model again. Let's take the Yij as the log implied volatility, I is the trading days, and say I took capital I, so 250 trading days, say per year, and Ji is an index of the traded options on daily I. So let me take this off, it's too long. So what do you think? Is J on the average? What is Ji? So how many observations did you see in this film per day? You have only short memory? I don't show you the film again. How many do you think are traded in Germany on the average these days? Per day? So really, that's why the talk is called Statistics in Finance and Computing. This goes into the computational limits also. The answer is about, nobody has read the transparencies, right, before. The answer is 5,000, roughly 5,000. 5,000 observations per day, intraday traded options on only the DAX. Yeah, these were DAX that I showed you, I forgot to say. Alright. The most active option market on the index is, by the way, the Korean. I learned recently. In terms of number of transactions per day. Okay, so for the ML, for the basis function, we consider two different setups. Namely, one where the xi is a two-dimensional vector containing the time to maturity and this forward moneyness. It's what you always saw on the axis that went from 0.8 to 1.2. It is the strike k divided by the future price ft. Or you can take also one-dimensional x, but I will show you all the analysis here with two-dimensional x. Okay? Now let's define estimates of these basis functions and these loadings in the following way. This is a so-called smoothed backfitting estimator. You find this literature in statistics, and recently it has been transported to econometrics and into finance. So you find papers, for example, in the Journal of Econometrics with this type of model. What you do is you take a smoother, so-called two-dimensional product kernel, and you penalize this distance between log implied volatility and the so-called additive model. And when you do that, you have to iterate between estimating. Here you estimate. You have to iterate between estimating m and estimating beta. Here you estimate m. Here you estimate beta. So you iterate always between two equations. One where you keep the m fixed, the other one where you keep the beta fixed. And the algorithm is described here, so you approximate for an appropriate initialization, for example, all the betas can be 1, you get an initial estimate of your basis functions, then you update it, then you estimate the M1 hat, and then you go to step 2 and you iterate until minor changes occur. Okay? So I give you a summary statistic here of this ODAX data, O option DAX, right, for the time frame from 1998 to 2001. So the shortest time to maturity was 0.028, the maximum 2 years. As you can see here, on the average, the data goes to 0.13. You see also the moneyness. The extreme moneyness was 1.8, and the minimal moneyness was 0.3. On the average, we are 0.98. And the implied volatility varied between 0.041 and 0.79, which is also kurtosis, where we also observe some kurtosis. Now, let us see how the model looks like for capital L equal to 4. So you have one invariant basis function. Remember, the model looks like that. Here's the model one more time. You have one invariant basis function, then you add some other basis function up, and then let's try to find an interpretation for these basis functions. So we have 4 dynamic basis functions. That means you get 4 loading time series, and the data that we look at is German DAX index options from 1998 to May 2001. Again, the logarithm of the implied volatility is the y variable that we're looking at. Here you see the first function M1 hat. So despite this effects here, you could say the first function gives you more or less the up and down movement. I will show this maybe from another talk if you allow me. I switch to another talk where I have a nice little picture of how this goes up and down. This might be yeah. If you have questions right now, please feel free to ask, right? Feel free to ask any questions immediately. Here, there it is. Okay. Interpret the first factor shock, the first function you can interpret as an up and down when you analyze the betas. Oops. Where's my control key? Here. The second function, you can see here, there's moneyness, there's maturity. The second function you can interpret as a skewness effect. Yeah? So the first function just goes up and down, it's responsible for the up and down movement of the blue surface or the red points in the molar surface. The next one for the tilt. Yeah? I'll show it to you here again. The next one is for the tilt. Right? So it tilts like this. Right? It's called skewness factor, on which you can then try to do skewness hedging, for example. And the fourth function, you see, it's sort of U-shaped. The fourth function picks up a twist shock, right? So you have the surface moves in and out. Right? So this is a very typical phenomenon that you observe also in principal components analysis of interest rate, for example, or also in principal components analysis for the implied volatility surface. But in this particular application, the power lies in having a better fit and the very flexible form for these functions. See to the right is a contour plot of these functions. Now, with these factors, now you have determined in this to determine deterministic index factor model, DSFM, the dynamic semi-parametric factor model. We have determined the functions m, right? And the betas tell you how much you go up and down, how much you skew, and how much you are being U-shaped. Yeah? And if you look at that over time, remember this time period was from 1998 to 2001. We see here for the first coefficient, for the second coefficient, and for the third coefficient, we see intertemporal structure. Yeah? So what you can do now with these loading factors, we have reduced now the whole problem of this film. The film, remember the film was a described a very complex dynamic. Okay? Now with this model, we have reduced it to a dynamic that we can describe by the three-dimensional time series. So this one is the dynamic of the first factor, this is the dynamic of the second factor, this one of the third factor, because the factors stay, of course, constant over time. So what do we do if we have such three time series? How do we analyze what is the typical econometric method to analyze the joint distribution of such a time series, the joint dynamic? We use, for example, vector autoregressive modeling. Exactly. This is a talk that I have. This is described in a paper that will come out in the Journal of Econometrics. But I will not go too much into too many details during this talk. I can just show you how unit root tests applied to this factor time series react. We see here the significance here when you apply ADF tests for beta 1, beta 2, beta 3. You see that you get possible unit root in the first one, but these are things that an econometrician can tell you sort of within a few minutes with reviews. He can tell you this analysis. So the statistical part here was to model and understand the dynamics via principal components or via these basis functions. The computational part is to find these this so-called dynamic semi-parametric factor. I would like to show you which software we use to do these computations. We developed it ourselves. The software is called Explore, and it can do things like, for example, making these blue surfaces. So let me try to find this. This is probably surface plot or implied molar surface plot. This is the help system here. Surface into plot. So I do here Control N, Control V, Alt E. If I'm lucky, I get just interpolates the surface. I interpolates the surface here. You see, this is the kind of program we use. You can then turn all this. This is a nice little feature that I wanted to show you is implied vol surf. I think that's what I want to show you. I want to show you how to calculate the implied volatility surface from kernel smoothing. Okay. So this is exactly how the plots look like. So we saw a sequence of these films. We should probably turn it a little bit or so to get in the right direction. But you see here the implied volatilities. Of course, here for computational reasons. So this was done on a very big Centrino. No, it's not even Centrino. It's a Pentium M. And maybe this is Centrino computer. So I cannot show you here the 5000. It will take much too long. But I just wanted to show you how we produce these blue curves. So what you can understand is, over this time, from 1998 to 2001, this is almost 2 years, right? We had to do for 5,000 points each day for each one, you have to analyze the residuals, etc. Now, maybe I can show you also a DSFM model in here. If I'm lucky, I find that as well here. No, it is not in here. I will have to show it to you after the break. Let me come back to the transparency and now talk about another computational method, namely how to calibrate the IDS to modern financial models like the Heston or Bates model. Is anybody knowing the Heston model here? Bates? One person knows, but maybe this person is professor already. Or from the students, anybody? Did you know what I did with this blue surface? Do you know kernel smoothing at all? You also don't know that. Okay, so let's make a small digression then, and let's have a look at kernel smoothing. So to do that, we'll use another trick here. You can do it on every computer, of course, that has Internet Explorer. Let us go to this web page where you find the program that is called explore.de. Can you read it? Can you read it from the back? Can you read it? Could you please read it for me? Hello? Could you please read this web page for me? This address, can you read this address? Then please sit down here so that you can read it. Otherwise you don't know it. Can you read it? Next one, where does it stop to be able to read? You should know this web page. Yeah? Sit down here so you can see that, because I would like to show you where to find lots of material on smoothing techniques. Yes? Yeah, sit down here and note this web page. Very good, thank you. Look, we have all the technology we have, all the books that we have, all the things that we did, statistics of financial markets, statistics of finance and insurance, are on this web page under the name ebooks. Yeah? So you go to ebooks. Okay. And then you go down. It's alphabetically ordered. There's applied quantitative finance, computer-aided introduction to econometrics, handbook of computational statistics measuring risk in complex stochastic systems. They are not in single parametric modeling. There's something that you could do. So you go to the HTML page. See that? Then what you want to do is you want to make blue surfaces, right? Are you interested in making a blue surface, you? Okay, good. How is it, the blue surface, how do I do it? We don't know yet, right? Okay, so this is a so-called non-parametric regression problem. We do that by using a so-called multivariate kernel estimator. Okay, multivariate kernel estimator. We go here, multivariate kernel estimator. And then we just wait until the formulas are there. So what we assume is we have some x variables, we have some y variables, this y variable, right? And y depends on the vector of the x variables plus some error. But so that the expected value of y given x is equal to this blue curve that I want to estimate, right? So I assume there's some underlying curve, model, surface, and the estimate is actually given here. The estimate is given here. Sorry. This is the estimate. This is how I estimated the blue surfaces. Yeah? It's the kernel estimator. One takes a weighted average of the y's in the neighborhood of x. A weighted average of the y's in the neighborhood of x. Yeah? Okay? Now, of course, I will not show there are some statistical properties that you are not interested in for the moment. I just show you how this would look like in terms of a local linear estimate. Okay. packet. You transport it into this nice little piece of software. You say glue it and execute it. Yeah? Now you can see this is the true function. This is the function that is estimating it with local linear estimate. And this one was local constant estimate, and this one was local linear estimate. Yeah? So what we saw was, go back here. The blue curves in the blue surface in the film were calculated with this formula. Yeah? Formula 468. This is called the so-called Nadaraya-Watson smoother. Yeah? Okay? And what you can this corresponds to locally estimate a constant, locally around x. You could also make a Taylor expansion around x, and you have a so-called local linear estimate. Okay, maybe I can offer you some more plots here. No, apparently not. Then let us go back to the books one more time, and let's have a look, for example, at applied quantitative finance. It will show you how this is connected to my talk in a second here. Implied volatility. We want to do analysis of implied volatility. Here we go. Okay. Now implied molar surface. Now, this is the typical molar smile when you keep the maturity fixed. Yeah, it would look like that. And the surface you should see here. Right? But we just calculated already the surface. Right? And the dynamic analysis is done with these dynamic semi-parametric factor models. You have seen it also in this film. Factor loadings. Maybe this takes too long to show you all this. Just keep in mind that this book here, Applied Quantitative Finance, has all these algorithms that I showed to you, just now. Now, the next part of my talk will come from this book, Statistical Tools in Finance and Insurance. This is the book. Just came out last March, so about a year ago. And it contains lots of useful material for insurance and finance guys. And I would like to show you the table of contents. Then I move to the next talk. Okay, so it contains stable distributions, extreme value analysis, and copulae, pricing of catastrophe bonds, implied turnover trees, and FFT-based option pricing. Yeah? And this part, FFT-based option pricing, you will also get from now in the next 15 minutes from via this PDF file. Okay? So let us now. You feel more confident now with smoothing after I've shown you how easy it is to do it? You have not understood it, but you feel more confident in applications, right? I hope so. And let me show you one more trick. One more trick I have to show you. The trick is the following. You can actually do this without using the software. If this place doesn't have a too tight security bound, you go to net-based data analysis here. And then you say start, and then it will open a Java window that allows you to do calculations via your browser. And all calculations will be done in Berlin, in Germany. That's the power of this. You have a question?
Did I the data size limitation.
Excuse me?
Data size limitation.
I didn't get your point. I didn't hear you.
Data size limitation.
Data size limitation for this Java server? No. There's no data size, of course. There's always a computational limitation.
I know the trial version only for several thousand data.
Yes, but this is not a trial version. This is computation on a big sun machine in Berlin. We need the trial version, but we are replacing now the trial version. The trial version has no limit anymore.
No.
No.
But it's fine in how many days?
Probably also not anymore. We changed the strategy.
Oh, okay.
But still, we hope that you buy it.
But you know what? I have checked that in Taiwan. We don't find any reseller here.
Sure. You don't find?
No.
We have one. I don't get that. Okay, but you saw here. Let me show you one more. Here's the Java interface. So you could calculate here 1 plus pi, right? For example, the answer is here. 4.14. Yeah. But you can, about that data limitation, I can calculate you the mean of 100,000 normal random variables, right? There's the answer. So Berlin generated 100,000 random variables, and it's easy, right? And you can configure this for your school. If you have a server running like this for your own school, you can make all these algorithms in sort of an Excel format. Let me show you this. So suppose you want to analyze these two columns, yeah? And you want to see here, say, where's this two-dimensional analysis? The scatter plot. You see scatter plot of these two columns, yeah? And in fact, it's the so-called decathlon data set. It's the 100-meter running time. And this is the long jump. Yeah? Okay, now a question to the students. 100-meter running time and long jump, is it positively or negatively correlated? The times, these are record times for Olympic decathlon. Is it positively or negatively correlated? Hello, students. Positively, I think it's negatively correlated. Right? Let's check it. You can just make a regression line, mean regression, and you see that. Because it's negatively correlated. Somebody who runs fast has a low 100-meter times, but he also jumps wide, right? So low 100-meter times, wide jumps. Okay, here's the correlation. So you can see if you are running 100 meters, say in 10.7, on the average you jump 7.3 meters. Yeah? Okay? In any case, enough. For Explore, let's now see the calibration of the IBS and option pricing via fast Fourier transform. Okay? So one of the basic problems, of course, is which model for the underlying instrument can replace well the derivative prices observed on the real market. So here you see competing models. This one is a regular geometric Brownian motion, and then you have one that incorporates jumps. Jump points, so-called leading crosses. So that gives you a blue curve. So black plus green gives you blue. Yeah? Alright? Now, the calibration part, because you have to fit the model that you invent for the underlying, you have to fit it to the observed data. And given a model for the underlying price process ST, for example, this Härdle and Bates model, you will see in a second, we estimate the parameters that minimize the distance between the IBS, because that's what you see on the market, right? And the IBS of the model. This involves numerical minimization, many evaluation of the function that have to be minimized, and it is very important to do this computation extremely quickly. So here you see in this talks about fast Fourier transform versus Monte Carlo. If you do fast Fourier transform, for fitting here, you see the strike, here you see the implied polar that you observe, the price is the same thing, and you see the FFT fit and the Monte Carlo fit. The FFT fit is the red curve, the Monte Carlo fit the points, it took only 0.015 seconds to fit the FFT by Monte Carlo to evaluate the risk-neutral expectation discounted from today of the future payoff. This 500 time steps took 36 seconds. Yeah? So this option pricing with FFT is based on an algorithm by Carr and Madan, who proposed this method to price option based on FFT. Of course, everybody knows FFT has very strong power in speed acceleration. And fortunately, the Fourier transform of the log price process is known for many models. Therefore, the FFT allows us to calculate prices for a whole range of strikes. So let's have a look how option pricing is actually done. Option pricing is done in the way that you take the future payoff, which is this one here. This is your future payoff. You hit it with the risk-neutral density of the log price. Yeah? And you discount it with e to the minus r tau. Yeah? Okay? And you can see here that this option price is unfortunately not square integrable, so we cannot directly apply the Fourier transform. That's why we consider a weighting function x of alpha k times ctk that allows us to do these computations in terms of Fourier transform. And of course then we'll change the a, or let alpha tend to be big to approximate the true option price. Okay, the fast Fourier transform, as everybody probably knows, of CT. CT is nothing else than the log, the log option price is given as in this formula here, psi t, right? It is square integrable, and we can get back the call price easily by making the inverse Fourier transform, that has just an I, we have a plus 1, we have a minus 1, I, bk, you integrate out with respect to b, that is the Fourier transform. Now, you can express this Fourier transform in an easy way. It is written here, and fortunately, if you do this at different strikes, Fourier transform as a whole immediately gives you a whole function at these numerical approximation values. For example, when you want to do n calls simultaneously with maturity capital T in strikes, these strikes here, you make a strike grid, so n can be very big, say 500 or so. It will immediately not at each strike one, but the whole grid of strikes will give back you the numerical approximation of the call price. So this is nothing else. You see, this thing here down here is nothing else than an integration to this, an approximation to this formula. Yeah? So the integral is replaced by sum. Here, right? Otherwise, everything identical right here. X minus alpha k, right? Divided by pi. Here, because it's asymmetric here, because I go from j equals 0 to n minus 1, I don't have to divide by 2 factors, just by pi. Okay. Now, the fast Fourier transform allows, of course, a direct application of the FFT, which is, as we know, a very efficient algorithm to computing sums of this type. Right? And our sum is of this type, but there are also some disadvantages in this numerical approach. There's some instability for fixed FFT parameters, alpha, eta, and n, and it's only applicable to European options, only applicable with a fixed T, not with a random stopping time. One can do several modifications, like using Simpson rule instead of the trapezoidal rule. That I did here. This is the trapezoidal rule, as you can see here, right? Because it just uses sum, could use the Simpson rule. That will stabilize it. But very important is that we get very quickly our calibration for very complicated models. One complicated model is this so-called Bates model, an extension of the Härdle model. Let's have a look at it. Where is it different from the geometric grounding motion? Let's pause here for a second and ask some of our younger colleagues here or students, where is it different? So, for some of you, this is the first time you see this model, right? So, who has not seen this model before? Okay, that means the majority has not seen this model before, right? Okay, but you have, before that, we made a little test, and then you said you have all seen the geometric grounding motion. So then you can tell me what's the difference to the geometric grounding motion. You have at least partial knowledge. Okay, once again, geometric grounding motion is TST, stock price ST unit T plus sigma BWT. And then nothing else. That's geometric grounding motion. So can you tell me now the difference, for example, of the so-called Bates model to the geometric grounding motion? You could simply answer, Professor, where you have said plus nothing, there is now something. That would be a perfect answer. Okay? Perfect answer. There is something. Okay? And what is there? First of all, there are two things. First of all, the Bates model, like the Härdle model, belongs to the model of so-called stochastic volatility models. Who has heard of stochastic volatility models here? Also, majority, yes? Majority says yes. Okay, good. Stochastic volatility means that sigma in the Black-Scholes model is replaced by a stochastic term. In this case, the stochastic term is another process that is governed by a stochastic differential equation with mean reversion term. This is a so-called mean reversion term. Right? And we have a Wiener process for the stock as the random shock, and we have another Wiener process for the variance here, and for the volatility, right? And they may be correlated also. Yeah? These two processes. Okay, if you don't have this plus dzt there, then it is called a Härdle model. Okay, so Härdle's big step into analysis of option or fitting the underlying stock was to write down the exact formulae, the exact asymptotics, the exact computational procedures to approximate for a so-called stochastic volatility model. So here are these equations. In the beginning with two independent Brownian motions, later it was generalized to correlated Brownian motions. And Bates here is additional idea of jumps of size. These jumps are so-called compound Poisson processes with log normal distribution of jumps. So here is the log normal distribution of the jump for a compound Poisson process. Okay, now fortunately the characteristic, because it's all with the normal distribution and the Wiener process, fortunately the characteristic function of this process is given, and the fast Fourier transform method can therefore be applied. Now the parameters that are to be estimated are lambda, the intensity of the jumps. Remember, here we have jumps, the green dye jumps. Right? The intensity of the jumps has to be estimated. The mean of the jumps, the deviation of the jumps, because this jumps are governed by this compound Poisson process. We have to determine the rate of mean reversion. Remember here, rate of mean reversion, this one here. We have to determine the average level of volatility, which is this one. We have to determine the volatility of volatility, this one. It's also, and the correlation of of the Wiener process, and the initial volatility. So these are the parameters we have to calibrate. So we do that by minimizing the following functions. We take ourselves nice little put that we observe, sorry, calls and puts from the market. These are from the markets here, right? And we calibrate them with respect to, these are market call prices, or like Wohler price, same thing. And these are the call prices from the Bates model that we calculate with this Fourier transform. And of course, this thing here has all these parameters in here. This is the parameter vector. Yeah? And then we have to minimize this function as a function of P. Yeah? Okay? So, for example, for the same stretch of data that you have seen before, we get the following estimates. And when we look at the implied Wohler smile, for example, we see the for tau equals 0.32, we see here the implied Wohler smile and the corresponding fit of the Bates model. Yeah? So it does not fit too badly. And all this is described in much more detail, as I have explained to you before, in this book, Statistical Tools in Finance and Insurance. Let's go there again and let me show you yet another trick. Okay, that's Statistical Tools in Finance and Insurance. Okay, here's the book. So all our technology is web-based, and I hope I can show you some pictures here. There's the Bates model, applications for this here.
Excuse me.
Yeah.
Can we use this model to American style option or other exotic option?
Yeah, then the FFT option price pricing is not suitable, as I said before, because we have that capital T is fixed. We have to have this fixed grid. We have to have this discounting. We don't have a, as you very well know, we don't have an explicit formula for the American options. We have the FFT is a numerical method to approximate this interval. So, exotic option, no problem if you give me the Fourier transform of your payoff. Also no problem. But just this is of course the critical point. So here you see this Wohler surface again. Here you see when you take not enough Fourier transform steps, so you get this chips phenomena. Let me just show you, maybe I can reproduce you this fit. These are several fits for the Bates model and the real market prices. 104, 104, Control N, Control V, and E. Okay? These are the fits. So now let me show you whether this works also like this. So you will see this in the break. So this is another trick. If we are lucky, then our server is running very well. And then you can even calculate this example without having the software downloaded. Yeah? So that means our server in Berlin calculates this fast Fourier option pricing directly for you. If you would have this technology here in Taiwan, then of course it would work in Taiwan. Let's see about this dealer in Taiwan. That's interesting. But there is one in Taiwan. I will find out. In the break. I make now a break. You can ask me questions once I found out the dealer, and then we can go. Actually, I know the dealer's webpage, maybe you can find it. Let's take a break, and I try to produce the dealer's webpage here, yeah?
Make a break. 10 minutes, and wait.